Hey there, calc folks, back here with another video where we're at the point in time where we need to introduce what are known as vector valued functions. What we need to introduce is something that behaves very much in a what we would say is a functional behavior, meaning that it takes as input one independent value and gives as output a corresponding dependent value, where there's only one dependent value corresponds to any given independent value. But we're going to now take this understanding of functional behavior and incorporate it into the realm of vectors, right? And what we're going to do here is we're going to look at a functional situation where we have a scalar independent value, just a scalar number as our independent value. And as that goes into what we call as a vector valued function as the independent value in that functional behavior, it gives as output a dependent value that is itself a vector in form. Right? That vector could be a two-dimensional vector in form. We might see that vector be a three-dimensional vector in form, or it could even be n-dimensional in its form. Right? But what we're referring to here is what we call a vector valued function. All right? If we where we open up our notes here is actually with some purpose. All right? Why do we look at vector valued functions? And what we just begin by taking note of is that if we're in two-dimensional space, right, to represent any path in two-dimensional space, we could use just a two-variable equation. Right? We are familiar with using a two-variable equation to represent a curved path in some two-dimensional space. Right? However, if we happen to be in an n-dimensional space where that space is greater than 2 in dimension, right? A multivariable equation, an equation that involves more than just a multivariable equation, more than one variable, will not describe a path in that space. And actually, any number of variable equation will not describe a path in that space, that n-dimensional space. Right? What a multivariable equation actually describes in higher dimensional space is what we call surfaces and hypersurfaces. Right? They don't represent paths or what we might think of as being curves in those spaces. Right? This is where vector valued functions come in. Right? Instead, in an for instance, in a three-dimensional space, a 1, 2, or 3 variable equation will actually describe what we call is a surface in that three-dimensional space. And in n-dimensional space, for n greater than 3, an equation with n or fewer variables will actually describe what is called a hypersurface. All right? In order to actually describe a curve in three-dimensional space, we would have to, or what we might say is a hypercurve in n dimensions, where n is greater than 3, a vector valued function is required. Vector valued functions are ways that we describe paths in n-dimensional space where n is greater than or equal to the value of 3. All right? Many curves in R sub 2 can also be described by a two-variable equation and a vector value function. If we also take note, this is not just true for three-dimensional space, but if we went back down into 2 dimensions, we could actually take these curves that are represented by a two-variable equation in this space and represent those curves using what we would say is a two-dimensional vector valued function. All right? 2 dimensions is the one unique case of space where both curves in that space, which are natural to that space, and vector valued functions in that, curves in that space can be described by both a two-variable equation and a two-dimensional vector valued function. When we move to 3 dimensions or higher, right, Multivariable equations describe surfaces or hypersurfaces. To describe paths in these spaces, we have to use a multidimensional vector-valued function. All right? So that's what these few notes at the beginning are getting into and are giving us some of our purpose here. All right? Consider the following portion of a curve in R2. If we take a moment, here is this curve in two-dimensional space. And actually, if I make it a little bigger here so we can see it in the video. Right? Here's our curve in this two-dimensional space. What we do notice, this might be a familiar looking curve. You'll notice at 0 for our x value, we are at 0. 1 for our x value, we're at the value of 1. If we're at 2 for x value, we're at the value of 4. And if we're at 3 for x value, it appears we're at the value of 9 up here along our y-axis. Right? It does appear that what we have is a portion of what we understand to be the square function, right? Or the multivariable equation y equals x squared. Each of our y values appears to be a value of x squared in this illustration, right? Well, I do believe we take note of that down below here, right? This curve could be described by the two-variable equation y equals x squared for values of x in this closed interval from 0 to 3. Right? For x values from 0 to 3, we have this portion of the curve forming. Right? And it could be described by this two-variable equation y equals x squared. Right? However, since it does exist in just two-dimensional space, r sub 2, or r superscript 2 here, right, this two-dimensional description of space, we could also describe it using what we call a vector-valued function. In this particular case, we might describe that vector-valued function being given by this vector description, t comma t squared. Right? Where this vector description, what we see going on here is it's taking on the form of a what we call a two-dimensional vector, where the components of that vector are themselves what? Variable in their behavior. The first component behaves as the variable t, and the second component behaves as the variable t squared. The x description, or the x component, behaves as the variable t, and the y description of this vector, the y component, is described by the variable t squared, where what is t? T, given here in our function notation, is describing the value of the independent variable. T represents what we call a parameter in the problem. Right? We have here parameter t, where t is this independent parameter, this independent variable that acts as an input into the function, where our function, we can see here using this function notation, is actually what we named the function r. Or what we should be more specific, because of the arrow notation above r, is indicating vector r. Right? This is the vector-valued function we sometimes call r bar of t. Right? Or vector r of t. Right? Where here vector r of t is a two-dimensional vector-valued function where its components at x and y, its x component and its y component in two-dimensional space, are described by the parameter t and t squared. For any given value of t, and here we might consider the values of t in that space from 0 to 3, right, we get a vector description of location. For instance, when t is 0, right, the x component, the x description of location is at 0, and the y component, the y description of location, is at 0. Whereas if I'm at t equal to 3, my x component for the description of location is at 3, whereas my y component at this description of location where t equals 3 would actually be at t squared. T being 3, that would be 3 squared, that would be at 9. So this vector would actually be pointing to this location right here on the parametric curve, or on this vector value function. And what I do take note there is a vector valued function is really just a parametric curve description that has been taken and placed into a vector description, kind of arranged into a vector description here. And we see this curve forms over values of t, starting here at t equal to 0 and all the way up to here at t equal to 3. All right? And what we do take note is both relationships illustrate position in this two-dimensional space. We can either describe that position using a two-variable equation, where y equals x squared for values of x in the interval from 0 to 3, or we can use this vector value description, right? Where r bar at t is equal to t comma t squared. Right? Now, if we scroll down here, right, I do believe I elaborate on that idea just a little further, right? We do note in the equation the y-coordinate in the xy coordinate, right, or the, well, yeah, the what we might call the y-ordinal, right, in the xy coordinate is at the value of the x-coordinate squared, right, or at the value of the x-ordinal squared. I might like that word a little better. Let's say ordinal. Right? For example, when x equals 2, y is 2 squared or equal to 4. That's what this equation is using to describe position in this two-dimensional space. Whereas if we look at the vector valued function, right? In the vector valued function, location is also described by the position vector in 2 dimensions relative to the origin, right? And it's dependent upon that additional parameter t. For example, when t is equal to 2, we are at this position r bar of 2. What is r bar of 2? Well, it's this vector description relative to the origin, 2 comma 2 squared, right? Because our vector value description for r bar of t is t comma t squared. And if t is 2, it's 2 comma 2 squared. Or the vector description 2 comma 4, right? Both the equation and the vector are pointing right to this location in our graph, right? When either x is equal to 2 in the equation or when t is equal to 2 in the vector valued functional description of this path in two-dimensional space. All right? I think from here I get into the formal definition. As for a formal definition of a vector valued function, right? We kind of go back to where I started, right? A vector valued function is a relationship between an independent scalar parameter, right? That's often that value of t that we use, right? And a dependent vector value, right? That dependent vector value represented by that value we've seen up above given by r bar of t. And t and r bar of t, right, are in this relationship such that for each independent scalar parameter, there corresponds just one dependent vector value. Right? For each independent value of the parameter t, there corresponds just one value of the vector valued function. Right? R bar of t. In this case, for the value of t equal to 2, there was only one location that was illustrating in our space, illustrating this functional relationship between the parameter t and this vector valued function r bar of t. All right? I do go a little further in the definition and incorporate our notation. All right? Commonly, t is used as our parameter, right? Letting t denote the independent scalar parameter, right? A vector valued function, right? Dependent upon the parameter t is denoted as r bar of t. Where in two-dimensional space, we might say r bar of t takes on this generic description, right? Where the x component in that two-dimensional description of location in space is itself a what we might think of as a scalar valued function of t, and the y component is itself a scalar valued function of t. This vector valued function of parameter t is nothing more than a multi-dimensional vector whose components are themselves scalar valued functions of t. We see that up here in this example, right? R bar of t was equal to t comma t squared. T and t squared are just scalar valued functions of t. This is a rather direct relationship between x of t and t. X of t is just equal to t, where here y of t is equal to t squared. Right? And this idea, in general, does expand into three-dimensional space, where in three-dimensional space, r bar of t could be thought as the three-dimensional vector-valued function x of t, comma y of t, comma z of t, where we add in this third component describing position in the three-dimensional space relative to the origin in the direction of what? Well, in that third direction, which we often say is the direction of the z-axis. All right. We're here, again, now x equal to x of t, y equal to y of t, and z equal to z of t are themselves just scalar value functions of the parameter t. All right. This idea does extend into n dimensions. If we were to have a four-dimensional vector-valued function, we might just add on a fourth dimension in our description of that vector. Right? If we had a fifth dimension, we might just add on that fifth dimension as a scalar valued function relative to the parameter. Right? Most of our work is going to happen in 1, 2, and 3-dimensional space. If we do go into n-dimensional space, what the vector valued function would be describing is what we call a hyperpath, or a hypercurve in that n-dimensional space, an n-dimensional hypercurve. All right. I do think I finish up here with just going back and summarizing this in our three dimensions, or sorry, in our two-dimensional example, right? Note in r bar of r bar of t equal to t comma t squared for t in this closed interval from 0 to 3, it is a vector valued function in r of 2, right, two-dimensional space, where these scalar value functions for x and y are these functions x equal to x of t equal to t for the first component, for the x component, and the y component, y of t, is simply equal to t squared, right? This value of x, or of t in the x component, is x of t equal to t, and this y component is y of t equal to t squared in our general description. And what it does describe is this path in two-dimensional space. This path in two-dimensional space starting at t equal to 0 and continuing off here to where t is equal to 3 in value. Moving in this forward orientation starting here and ending here. All right. Now, I do follow this up with a couple of quick examples that I'd like you to take a look at. What I will likely do is make another quick video covering these three examples. Let me just go ahead and pull these all up into view here, and we'll go through them real quick as you start to approach them on your own here. You will note here is this two-dimensional vector valued function where x of t is equal to t plus 3 and y of t is equal to the square root of t plus 5. What I would like you to do is to look at this and consider the domain. Maybe make a table of values for r bar of t over some values of that domain. And then consider sketching the graph over this domain, actually indicating some orientation of the curve in that graph, putting some arrow into that curve, some directional indication as to what would be forward orientation, and then to come along and determine the corresponding rectangular equation involving those variables x and y. If this exists in two-dimensional space, there must be some corresponding rectangular equation that also describes it. Can you find that corresponding rectangular equation? I also give you that to you similar analysis here for this vector valued function, where here I'm only interested in values of the parameter t in this closed interval from 0 to 2 pi. Now you will notice this does incorporate a little trigonometric function to our work, and this interval from t from 0 to 2 pi does look a little familiar, hopefully, with the trig, so you know that you're going to see some interesting behavior happening here in your analysis. All right? And here, in this third example, what we have is a three-dimensional vector valued function, so we are incorporating that third component, where we also have some trig functions being just incorporated with a linear function here, an identity relationship between x at t and t. All right? Where I want you to do a very similar analysis. Now, what you will notice in this analysis is I don't have you determine the corresponding rectangular equation. Because we are in three-dimensional space, there is not a equational description of what would be this path in space. All right? But I will come back here, hopefully with a quick video, and go through this analysis with you, folks. But I want to give you a little bit of a chance to get a head start on me. All right? So, folks, that is the first bit of lecture over vector valued functions. You might want to go out and also take a look at the book and see what the book has to say. You might also go out there and seek out some other YouTube videos that might aid you in some of this. And like I said, I'm going to have another quick video here working through the analysis of these examples for you. And there are some other tools that I'm going to bring up along the way that are also going to certainly help us with all this. And this is just the beginning, just the introduction to all this, folks. What we are going to see is with any function, right, calculus can be applied. Right? The idea of a limit can be applied. Right? And if we can apply a limit, well, what do limits lead us to? Derivatives. Right? So we'll be able to take derivatives of vector valued functions. And what does the idea of a derivative lead us to? Antiderivatives. So antiderivatives can be applied to vector valued functions. And there's going to be uses and applications of those ideas that are all going to develop in the next couple of videos. So stay tuned for all that, folks. This is just the beginning. This is my first video. I hope you're hanging in there. And I will be back with more. See y'all then.